Have you ever found yourself trying to figure out something really complex? Maybe diagnosing a tricky network problem, or even just deciding what car to buy, and you kind of break it down, right? Step by step. You think, okay, if this is true, then maybe that's the answer. Ooh, what if machines could do that too? Make decisions using that same kind of clear step by step logic, almost like how we think sometimes. Okay, let's unpack this. Today, we're doing a deep dive into, well, one of the most fundamental and honestly really intuitive techniques in machine learning, decision trees. We've pulled together a whole stack of fascinating insights, practical examples, real world applications, all the good stuff. And we're going to distill it down into the most important bits for you, our listener. Think of it like a shortcut, a way to get properly informed about something that's just foundational to modern AI. So over the next little while, we're going to explore the basic idea behind these tree things, what makes them tick, how they actually think. We'll look at how popular tools, especially Python's Sklern library, bring them to life in code, which is pretty essential these days. Then we'll get into the details, the parameters, those knobs and dials that control how they behave, and how to actually see what they're doing, visualizing these decision paths, peeking inside the logic. Importantly, we'll tackle their big weakness, that famous Achilles heel. How do we avoid, overfitting, where the model looks great on old data but just bombs on new stuff? And of course, we'll ground all this theory in some cool, maybe surprising real-world examples. Everything from perfectly classifying, like delicate flowers.
The iris data set, yeah.
Exactly. To grappling with predicting house prices, which is always messy, and even estimating the age of a sea snail, which, believe me, sounds simpler than it is.
It's definitely more complex than you'd think.
So yeah, we're here to guide you through it. Point out the surprising bits, the aha moments. Let's get started. Let's decode these decision trees. So let's start right at the beginning. The intuitive idea. When I hear decision tree, my mind jumps to like those flow charts you see. Or maybe those old choose your own adventure books. Is that basically what we're talking about here in machine learning?
That's actually a really good way to think about it, yeah. At its core, a decision tree is very much like a flowchart.
Okay.
Formally speaking, though, we'd call it a non-parametric supervised learning method. Let's break that down a bit.
Yeah, please do. Non-parametric.
Right. Non-parametric means it doesn't make strong assumptions about how your data is distributed beforehand. Unlike, say, linear regression, which assumes a straight line relationship. Trees are more flexible, they can adapt to weird shapes in the data.
Ah, okay. So they don't force the data into a box it doesn't fit.
Pretty much. And supervised just means it learns from examples where you already know the right answer. You give it input features and the correct output labels, and it learns the rules from those pairings.
Got it. Labeled data.
Exactly. And what makes them stand out, I think, is their incredible versatility. They're really good at building both classification models.
Like spam or not spam?
Precisely. Predicting categories or, which species of flower is this. But they can also build regression models.
Which is for predicting numbers, right? Like a price.
Exactly. Predicting continuous values, like the price of a house or maybe someone's age. And the core idea, the principle behind both, is the same. The tree predicts a label or a value based on a set of rules it learns directly from the features in your training data.
So it looks at the data and figures out the rules itself.
Yes. It breaks down what might seem like one big, complex decision into a whole sequence of simpler, smaller choices, like sorting through the data step by step based on feature values.
So it's essentially building a set of clear if-then rules for us. If it builds those rules, does that make them easier to understand, like compared to some other machine learning models that feel a bit like black boxes?
That's precisely one of their biggest selling points, their interpretability. Because the model is those if-then rules, you can literally follow the path down the tree for any given input and see exactly why it made a certain prediction.
Okay, that's pretty powerful.
It really is. You don't often get that direct insight with, say, complex neural networks. Now, the potential catch, as you might guess, is if the tree gets really, really deep.
Ah, then the rules become super complicated.
Exactly. You could end up with hundreds or thousands of very specific rules, and then it maybe loses some of that easy transparency. It's a trade-off.
Yeah.
But the way these rules are built has definitely evolved. There's a history here.
Oh, like different versions of these tree algorithms.
Yeah, absolutely. The real foundation was an algorithm called ID3. That stands for Iterative Dichotomizer.
Catchy name.
Huh, yeah. It was groundbreaking because it created multi-way trees. That means a single decision point, a node, could split into more than 2 branches, maybe 3 or 4, based on the different categories of a feature.
Okay.
It was a great start, but it had limitations. It struggled a bit with continuous numbers, and Missing data wasn't handled smoothly.
So room for improvement.
Definitely. So next came C4.5. This was a big step up from ID3, tackled a lot of those issues. And a really key improvement in C4.5 was its built-in ability to convert the trained tree directly into a set of human-readable if-then rules.
Oh, so it explicitly gave you the rule book.
Exactly, like a detailed playbook.
Yeah.
This was huge for interpretability, for understanding why the model was doing what it was doing. Made debugging much easier, too.
Can imagine.
Then there's C5.0. This is actually a later, optimized, and proprietary version of C4.5. It's much more efficient, uses less memory, builds smaller rule sets, and generally runs faster. Really important for tackling bigger data sets practically.
Right, efficiency matters when data gets large.
Absolutely. And that brings us to a really critical one, especially for today's discussion, CART. That stands for Classification and Regression Trees.
Okay, the name says it all there.
Pretty much. Unlike some earlier ones that focus mainly on classification, CART handles both classification and regression tasks. Super versatile.
So one algorithm for both types of problems.
Yes, but here's a key difference from C4.5. CART doesn't directly compute those rule sets in the same way. Its main focus is on making binary splits.
Binary, meaning each decision point only splits into two branches.
Exactly. Every single node splits into just two paths. True or false, yes or no. This binary structure makes it very efficient, especially for large data sets. And it's actually the foundation for more complex models like random forests, even though you might need an extra step later to sort of export the rules textually.
Okay, so CART is efficient, handles both tasks, uses binary splits. That sounds like a solid foundation.
It really is. It's a pragmatic choice, very robust.
So that background is super helpful. But, for people actually doing machine learning day to day, how does this translate into the tools they use? Like, if I'm using Python, I'm probably using Sklearn. How does Sklearn implement these decision trees?
Right, Sklearn. It's pretty much the cornerstone for machine learning in Python, isn't it?
Mm.
And yeah, it has excellent support for decision trees.
So what's under the hood in Sklearn? Which version are we talking about?
Good question. Sklearn uses an optimized version of the CART algorithm, the one we just discussed.
Okay, so binary splits, classification, and regression.
Exactly. That binary split nature is consistent across Sklearn's implementation. Now, there's one really important caveat you need to remember when using Sklearn trees.
Oh, what's that?
Currently, its decision tree implementation does not directly support categorical variables.
Wait, really? So features like male, female, infant, like in that abalone example, Sklearn can't handle those directly in a tree?
Not directly, no. If you feed it categorical data without pre-processing, it'll likely treat them as ordered numbers, which can lead to nonsensical splits.
So what do?
You have to pre-process them. The standard approach is one-hot encoding. You essentially convert each category into its own binary 0 or 1 feature. So sex might become 3 features: sex male, sex female, sex infant.
Ah, okay. So an extra step, but manageable.
Exactly. The common pre-processing step anyway. Now, for actually using the trees in Sklearn, there are 2 main classes, or estimators, as Sklearn calls them.
Right.
For classification, predicting categories, you'll use Sklearn.tree, decision tree classifier.
Makes sense.
And for regression, predicting continuous values, you use Sklearn.tree, decision tree regressor.
Also makes sense. Classifier and regressor.
Yep. And the really convenient thing is that they share almost all the same parameters, those knobs and dials we need to control them. The main difference is the criterion they use to decide on the best split, which we should definitely talk about.
Okay, yeah, let's get into those parameters. You called them knobs and dials. I like that. So what are the key ones we need to know about? How do they let us shape the tree and, stop it from going wild?
Absolutely crucial. These parameters are how you control the complexity and prevent overfitting. Let's go through the big ones. First, there's splitter. This tells the algorithm how to choose the split at each node. The default is best.
That sounds good.
It usually is. It means the algorithm looks at all possible splits across all features and picks the absolute best one according to your chosen criterion. It's thorough.
Okay. Is there another option?
Yes, random. With random, it only considers the best split among a random subset of features at each node. This can be faster for huge data sets and is actually used deliberately in things like random forests to add diversity. But for a single tree, you usually stick with best.
Got it. Best is the default. What's next?
Probably the most important one for controlling complexity: max depth.
Ah, the maximum depth, like how many levels the flowchart can have.
Exactly. How many if-then steps it can chain together. If you leave it as the default, which is none, the tree will just keep splitting
Until
every leaf node is perfectly pure, All samples in it belong to the same class for classification or have very similar values for regression. Or until a node has fewer samples than another parameter called min-sample split.
And letting it grow indefinitely sounds like overfitting fuel.
Big time. That's how you get trees that memorize the training data perfectly but fail on new data.
Yeah?
So you almost always want to set an integer value like max step 5 or max step 10 to limit its growth. It's often your first and best defense against overfitting.
Okay, limit the depth. Makes sense. You mentioned min-sample split.
Yep. That's the minimum number of samples required in a node before the algorithm will even consider splitting it further. The default is 2.
Only 2. That seems low.
It's quite low. It means even if a node only has 2 samples, the tree might try to split them. You can set this higher either as an absolute number, say min-sample split 10, or as a percentage, like min-sample split 0.05 for a 5% of the samples.
And why adjust this?
It's another overfitting control. A very small value, like the default 2, can lead to splits based on tiny groups of samples, maybe even outliers or noise. A large value can prevent the tree from learning useful patterns if it stops splitting too early. That's called underfitting. Finding the right balance is key.
Right, the sweet spot. Is there another related one?
Yes, min-sample sleeve. This is subtly different. It's the minimum number of samples required to be in a leaf node. The default is 1.
So a leaf can contain just one sample by default.
Yes. This parameter says that for a split to be considered valid, both of the resulting child nodes must have at least min-sample sleeve samples in them.
Ah, okay. So it looks ahead to the result, the split.
Exactly. If you set min-sample sleeve 5, for instance, a split won't happen unless it creates 2 new nodes, each containing at least 5 samples. Like min-sample split, it helps prevent overfitting by stopping the tree from creating leaves for tiny, potentially noisy groups or individual outliers. It gives you control over the final granularity of the tree.
Okay, those seem like really important levers. Max depth, min-sample split, min-sample sieve. You also mentioned criterion earlier as the main difference between the classifier and regressor. What exactly is that measuring? How does the tree mathematically decide which split is better?
Great question. The criterion is the heart of the split decision. It's a mathematical function used to measure the quality of a potential split. Essentially, it quantifies how well a split separates the data or reduces impurity or variance in the resulting child nodes.
Impurity, like how mixed up the classes are in a node.
Exactly. For classification tasks, the goal is usually to make the child nodes as pure as possible, ideally containing samples of only one class. Sklearn gives you 2 main criteria for this. First is Jenny. This is the default choice. It measures Jenny impurity. A Jenny score of 0 means perfect purity. All samples belong to one class. The algorithm tries to find the split that results in the lowest average Jenny impurity across the 2 child nodes.
Okay, minimize Jenny impurity. What's the other one?
The other is entropy. This uses concepts from information theory, specifically measuring information gain. Entropy measures the disorder or uncertainty in a node. A good split is one that maximally reduces this uncertainty, meaning it provides a high information gain.
So, Durrani minimizes impurity, entropy maximizes information gain. Is one generally better?
Honestly, in practice, they often lead to very similar trees. Durrani is slightly faster to compute, which is why it's the default. Sometimes entropy might lead to slightly more balanced trees, but the difference is usually small. Worth trying both if you're fine-tuning.
Okay. And what about for regression tasks? We're not measuring class purity there.
Right. For regression, we're predicting a number, so the criteria focus on minimizing the variance or error of the values within the child nodes. The goal is to make the values within each node as similar as possible.
Makes sense. What are the options?
The default and most common is squared error. This used to be called EMS. It aims to minimize the mean squared error, MSE, within each child node. It heavily penalizes large errors.
So minimize squared differences from the mean.
Yep. Then there's Friedman's. It's a modified version of MSE that includes a correction factor, sometimes used in ensemble methods. Might give slightly better splits in some cases.
Less common, maybe.
A bit less common for single trees, yeah. Another option is absolute error. This minimizes the mean absolute error, MAE, instead of squared error.
So it doesn't square the errors.
Correct. It just takes the absolute difference. This makes it less sensitive to outliers compared to MSE because it doesn't blow up large errors by squaring them. Could be better if your data has extreme values.
Interesting trade-off. Any others?
There's also Poisson. This one's more specialized, designed for situations where your target variable represents counts like number of website clicks or number of fish caught. It uses a criterion based on reducing Poisson deviance.
Okay, so specific criteria depending on whether you're classifying categories or predicting numbers and even the type of number. That's quite a bit to control.
It is, but having these options lets you tailor the tree very effectively to your specific problem and data. Hashtag tag3. Visualizing and understanding the tree's decisions.
Okay, so we've got these algorithms like CART implemented in Sklern, and we have all these parameters: max depth, min sample sleeve, the criterion that shape how the tree grows and makes decisions. It sounds powerful, but maybe a bit abstract with all these numbers. How do we actually see what the resulting tree is doing? How do we visualize its logic to understand it, or maybe explain it to someone else?
That's one of the best parts about decision trees. Visualization is incredibly straightforward and powerful. Unlike trying to visualize, say, a deep neural network, you can literally draw the decision
We
tree.
like actually get a picture of the flow chart.
Exactly. Sklern provides a great tool for this, sklern.tree.plottree. It's a utility function designed specifically to create these visualizations.
Cool. What do you need to give it?
You mainly need to give it the trained decision tree model itself. But to make the plot really useful, you'll want to provide a few other things. You can set max depth just for the visualization. So even if your tree is very deep, you can choose to only display the top, say 3 or 4 levels to get the main structure without overwhelming detail. Crucially, you should pass feature names. This is a list of your actual feature names, like petal length or median income. This makes the plot readable. Instead of seeing x2 equals 5,000, you'll see median income equals 5,000. Huge difference in understanding. For classification, you'll want class names too, like Setosa, Versicolor, Virginica. This labels the predicted class in the nodes. And you can tweak things like label to show impurity values, BE or MSE, in each node, which helps understand split quality.
Okay, so you feed it the train tree and some labels. What does the picture actually show you? What's in each box or node?
Each node in the plot gives you a snapshot of the decision process at that point. First, you see the splitting criterion, the rule used at that node, like petal length equal 2.45. Then you'll usually see the impurity measure, conjoined for classification, or squared error for regression at that node. Lower values are better, purer. You get the samples count. How many training examples actually reached that specific node? You see the value. This is really important. For classification, it shows the distribution of classes among the samples in that node. For example, 0, 45, 5 means 0 of class 0, 45 of class 1, 5 of class 2. For regression, it shows the average target value, for e.g. average house price, for the samples in that node. You see the value. And finally, for classification, it often explicitly states the predicted class for that node if it were a leaf.
Wow, okay, so each node is packed with information about the rule, the data that got there, and the outcome. That sounds incredibly useful for interpretation.
It really is. You can visually trace paths down the tree and understand exactly how a prediction is made.
So we can see the tree structure. But you mentioned earlier that some algorithms like C4.5 could output the rules as text, like if X, then Y. Can Sklern's CART trees do that too? Can we get that explicit if-then playbook? That seems super useful for documentation or maybe even implementing the logic elsewhere.
Yes, absolutely. While CART itself doesn't natively focus on rule set generation like C4.5 did, Sklern provides a way to extract that information. You can use the export text method.
Export text, okay.
You give it the train tree and optionally the feature names, and it generates a text-based representation of the tree's rules. It looks exactly like those nested if-else conditions you'd expect.
Like, if petal length equals 2.45, then classify as setosa, else if petal width 1.75, then classify as versicolor.
Precisely like that. It gives you a clear, human-readable, logical flow that describes the decision process step by step. Really handy for documentation, explaining the model, or even, as you said, potentially translating that logic into another system if needed.
That's fantastic for understanding how it decides. But what about which factors are most important? In a data set with maybe dozens or hundreds of features, how do we know which ones the tree relied on most heavily?
Another great advantage of trees. They give you a direct measure of feature importance.
How does that work?
After you train the tree, you can access an attribute called feature importances. This gives you a score for each feature, usually normalized so they sum up to 1.
And what does the score represent?
It basically quantifies how much that feature contributed to reducing impurity across all the splits in the entire tree where that feature was used. Features that are used for splits higher up in the tree or are used in splits that result in a large reduction in impurity, a big information gain or Giardini reduction, will get a higher importance score.
So a higher score means the feature was more influential in the tree's decisions.
Exactly. It tells you which features the model found most predictive. This is incredibly valuable for understanding your data, for potentially simplifying your model by focusing on key features, and for explaining to stakeholders which factors are driving the predictions.
Okay, this all sounds incredibly powerful and interpretable, but there's always a but, isn't there? We hinted at it earlier. Decision trees have this notorious reputation for, well, getting things wrong in a specific way. What's their big Achilles heel, and critically, how do we manage it in practice?
You've nailed it. The biggest challenge, the thing you always have to be mindful of with decision trees, is their tendency to overfit the training data.
Overfit. Can you remind us exactly what that means in this context?
Sure, overfitting is when the tree learns the training data too well. It doesn't just learn the general patterns, it starts learning the noise, the random fluctuations, the specific quirks and outliers present in the particular data it was trained on.
So it basically memorizes the training set,
Yeah.
including all its imperfections.
That's a great way to put it. It creates rules that are incredibly specific to those training examples. Think of a tree that grows so deep, it has a separate leaf node for almost every single training data point.
And the consequence of that.
The consequence is that while the tree might look brilliant, maybe even get 100% accuracy, on the data it was trained on.
It falls apart on new data.
Exactly. It performs poorly on new, unseen data because those hyper-specific rules it learned don't generalize. The noise and quirks it memorized aren't present in the new data, so its predictions become unreliable, sometimes wildly inaccurate. An overfit model is essentially useless in the real world.
Right. So how do we stop this? How do we encourage the tree to learn general patterns instead of memorizing noise?
There are two main strategies, often called pruning techniques, because they involve limiting the tree's complexity, kind of like pruning a real tree.
Okay. Pruning. What's the first way?
The first is pre-pruning. This means stopping the tree's growth before it becomes too complex and starts overfitting.
How do you do that? Is it just setting max depth?
That's a key part of it. Using parameters like max depth, min sample split, and min sample sleeve is pre-pruning. You're setting constraints beforehand to prevent the tree from growing too deep or splitting on tiny groups of samples.
Okay. But how do you find the right values for those parameters?
That's where hyperparameter search comes in. Tools like Grid Search CV and Sklern are perfect for this. You define a grid, a range of possible values. For parameters like max depth, for example, try depths 3, 5, 7, 10, and min sample split, for example, try 5, 10, 20. Grid Search CV then systematically trains and evaluates a tree for every single combination of those values, using cross-validation.
And it tells you which combination worked best.
Exactly. It finds the combination that performs best on the held-out validation data, not just the training data. This helps you find parameter settings that promote good generalization and prevent the tree from overfitting in the first place.
Okay, so pre-pruning sets limits beforehand, often found using search techniques. What's the other strategy?
The other strategy is post-pruning. This is kind of the opposite approach. You first let the tree grow quite deep, maybe even fully, potentially overfitting it initially.
Let it overfit first. That sounds risky.
It sounds counterintuitive, but then you prune it back. You simplify the already grown tree by removing branches or nodes that provide relatively little predictive power for the amount of complexity they add.
How do you decide which branches to cut?
The main method in Sklern is called cost complexity pruning. It's controlled by a parameter called CC-alpha. Basically, it looks at the trade-off between the tree's complexity, number of leaves, and its accuracy. As you increase CC-alpha, the algorithm identifies and removes the weakest links, the splits that offer the least improvement in accuracy for the complexity they add. It finds a sequence of pruned trees, and you can use cross-validation to select the one with the best generalization performance.
So pre-pruning stops growth early. Post-pruning grows big, then cuts back. Is one better?
It depends. Pre-pruning can be faster, as you don't grow the full tree. Post-pruning might sometimes find slightly better trees because it considers the fully grown structure before simplifying. Often you might use a combination, set some reasonable pre-pruning limits, like a maximum depth, and then potentially apply some cost complexity pruning as well.
Okay, pruning is key. Beyond that, are there other general tips or best practices for working with decision trees effectively? Things to keep in mind about the data or the process?
Definitely. A few practical things can make a big difference. First, think about the ratio of samples to features. Trees can really struggle and overfit if you have a lot of features compared to the number of samples, like thousands of features and only 100 data points. That's asking for trouble. You generally want a good number of samples per feature for the tree to find robust patterns.
So more data is good, especially if you have many features?
Pretty much, which leads to the second tip. Consider dimensionality reduction before training. Techniques like PCA, principal component analysis, or using feature selection methods can help.
How does that help the tree?
It can reduce noise by removing irrelevant or redundant features. It can also combine features into more informative components. Giving the tree a smaller set of more potent features to work with often leads to a simpler, better generalizing, and sometimes more interpretable tree.
Okay, simplify the input first. Good idea. What else?
When you visualize the tree using plot tree, start small. Don't immediately try to plot a tree with max depth 20. Start with max depth 3 or 4.
Why?
It helps you get a feel for the most important splits happening near the root. Does the logic make sense? Are the main features being used as you expect? This is a great sanity check before you let the tree get more complex. You could iteratively increase the visualized depth as you understand the structure.
Iterate on visualization. Got it.
Another big one, especially for classification. Check for dataset imbalance. If you have, say, 99% normal cases and only 1% fraud cases, the tree might just learn to always predict normal because that gives high accuracy.
But it completely misses the important rare cases.
Exactly. So if your classes are imbalanced, it's often a good idea to balance the dataset before training. You can use techniques like oversampling the minority class, making more copies of the rare examples or creating synthetic ones, or undersampling the majority class, removing some of the common examples. This helps the tree pay appropriate attention to all classes.
Balance the data so the tree doesn't get biased.
Right.
And finally, just reiterate the careful use of min-sample split and min-sample sleeve. They are powerful. Set them too small, and you'll likely overfit, creating rules for tiny, noisy groups. Set them too large, and you'll underfit, preventing the tree from learning enough detail. Finding that balance, often through that hyperparameter search we talked about, is really key.
Okay, those are some really solid practical tips. It's not just about the algorithm, but how you prepare the data and tune the controls.
Absolutely. It's an iterative process. All right, we've covered the theory, the implementation in Sklearn, visualization, feature importance, and crucially, how to avoid overfitting with pruning and other best practices. Now let's get our hands dirty and see how these decision trees perform in action. We've got a few cool case studies lined up. First up, let's revisit that classic you mentioned, the iris flower dataset. It's famous in machine learning, right? 3 species of iris, trying to classify them based on measurements like petal length and width. How did a decision tree handle this relatively clean, simple problem?
Yeah, Iris is the hello world of classification data sets almost. The data is clean, the classes are quite distinct. We've got features, sepal length, sepal width, petal length, petal width. The goal, predict one of 3 species, Setosa, versicolor, virginica.
Yeah.
So the setup was straightforward. We used a pipeline. First step, min-max scaler to scale all features to be between 0 and 1. This prevents features with larger values from unfairly dominating the splits. Second step, a decision tree classifier. We started simple, setting an initial max depth of just 3.
Okay, scale the data, build a shallow tree. What happened?
The results were, well, pretty stunning.
Yeah.
Almost anticlimactic in how good they were.
Oh, perfect score.
Pretty much.
Huh.
When we evaluated on the held-out test set, the confusion matrix was perfect.
Yeah.
All the predictions landed exactly on the diagonal. 0 misclassifications.
Wow, none at all.
None at all.
Yeah.
The classification report confirmed it. Precision, recall, and F1 score were all 1.0 for every single class. It just nailed it.
That's incredible. So for this kind of well-structured data, a simple decision tree can be incredibly effective right out of the box. What features did it find most useful to get that perfect score? Did it even need all of them?
That's where feature importance comes in handy. The analysis showed that petal length was overwhelmingly the most important feature. It got a score of about 0.935.
Whoa, 93.5% just from petal length?
Yeah, the vast majority of the classification power came from just that one feature. Petal width was next, contributing the remaining 6.5%.
And the sepal measurements?
Yeah.
Length and width.
For this particular tree, max depth 3, their importance score was 0. The tree didn't use them at all. It found it could perfectly separate the classes just by looking at the petals.
Fascinating. It zeroed in on the most informative features. Did you try tuning the hyperparameters just to see if it changed anything?
We did. We ran grid search CV exploring max depth from 1 to 5 and min sample split from 2 to 10, using F1 macro as the score to optimize.
And the best combination.
The best parameters found were max depth 4 and min sample split 2, so slightly deeper than our initial guess. But when we retrained with these best parameters,
Still perfect.
still perfect. Another perfect confusion matrix on the test set, It just confirms that for this particular data set, the classes are so well separated based on petal dimensions that a relatively simple decision tree is a robust and extremely accurate solution.
Okay, from the clean, almost easy world of iris, let's jump to something much messier. You mentioned predicting the age of abalone snails. That sounds less straightforward. And the traditional method involves cutting shells and counting rings under a microscope. That sounds tedious.
It's described as boring and time-consuming, which is often where machine learning tries to help. Can we predict the age or number of rings, which is closely related just from external physical measurements?
So what's the data like?
It's definitely more complex. We have about 4,177 examples with 9 features. It's a mix. One categorical feature, sex, male, female, or infant.
Which we know sclerin trees need one hot encoding for.
Precisely. And then several continuous numerical features. Length, diameter, height, and various weights. Whole weight, shucked weight, meat only, visceral weight, guts, and shell weight.
And the target, what are we predicting?
The target is rings, the number of rings in the shell. Age is technically rings plus 1.5 years. It's a discrete number, but there could be quite a few rings, up to 29 in this data set. So we initially decided to treat this as a 29-class, multi-class classification problem.
29 classes, that sounds challenging right away.
It is, and data exploration revealed more challenges. Plotting histograms of the ring counts showed a big imbalance. Lots of abalone, around 9-11 rings, but very few with, say, more than 15 or less than 5.
So many rare classes. The model might struggle with those.
Definitely. We also found very high correlations between some features, like length and diameter were almost perfectly correlated, 0.99. Some weights were also highly correlated, 0.97. This multicollinearity can sometimes confuse models.
Redundant information.
Exactly. Box plots also showed lots of outliers in the weight features, and critically, we found that the height feature had some values recorded as 0, specifically for infant abalone. 0 height isn't possible, so that clearly indicated missing or bad data that needed fixing.
Okay, so messy data. Mixed types, imbalanced classes, high correlation, outliers, missing values. Sounds like a real-world data set. What did the pre-processing pipeline look like?
It had to be quite comprehensive. 1. Handle the missing height values. We imputed the 0 heights by filling them with the average height specifically calculated from the infant abalone group. 2. Use a column transformer for mixed types. 2. Use a column transformer for mixed types. Numerical features went through simple imputer just in case, using a constant fill strategy, and then standard scaler to get them on the same scale. 2. Use a column transformer for mixed types. The categorical sex feature went through one hot encoder to create those binary sex M, sex F, sex I columns. 2. Use a column transformer for mixed types. 3. Finally, feed that cleaned, processed data into a decision tree classifier, again started with max step 3.
A lot of prep work before even training. So after all that, how did the initial max step 3 tree perform on this much harder problem? Was it better than guessing?
Well, it was better than random guessing, but not by a huge margin. The initial training score was only 0.245.
So about 24.5% accuracy on the data it trained on.
Roughly.
Yeah.
And the performance on the unseen test set was similar. Overall accuracy was only 25%. Cross-validation confirmed this, giving around 25.5% accuracy.
Oof, not great.
No. The confusion matrix showed a lot of errors, often predicting classes close to the true one, but rarely getting it exactly right. And the classification report was revealing. Many of the rarer ring counts had 0 precision and 0 recall. The model simply couldn't predict those classes at all, likely due to the imbalance. The best performance, highest F1 score, was for ring count 7, one of the more common classes.
So a much, much tougher nut to crack than iris. Clearly highlights the difference data quality and complexity makes. Did hyperparameter tuning manage to squeeze out much more performance?
It helped, yes. We ran grid search CV again, this time exploring max depth from 1 up to 9, and min sample split from 2 to 10. We used recall macro as the scoring metric because of the class imbalance. We wanted to ensure it tried to do well across all classes, not just the common ones.
And the best settings it found.
The best combination turned out to be max depth 5 and min sample split 4. A slightly deeper tree again.
Did that make a big difference to the score?
It resulted in an improved model score of 0.27, up from the initial 0.25s. So accuracy nudged up to 27%.
Okay, so an improvement, but still not super high accuracy overall.
No, it shows the limitations. This is inherently a difficult problem for classification, especially with so many imbalanced classes. A single decision tree, while interpretable, might just not be powerful enough here. Maybe ensemble methods or framing it differently would be better. And that leads to a challenge for you, the listener. If you are tackling this, you could try evaluating this tuned classifier on the test set, look at the confusion matrix where it's still struggling, but also consider this. What if you treated it as a regression problem instead? Predicting the number of rings directly, rather than classifying into 29 bins? Would decision tree regressors do better? It's a common approach for this dataset and often yields more useful results given the low classification accuracy. Something to experiment with.
Okay, that abalone example was a great reality check. Let's shift gears now from classification to regression, predicting a continuous number. We're looking at the California housing dataset, predicting house prices. This feels like something a decision tree could be good at, right? Lots of factors influencing price, maybe nonlinear relationships.
Exactly. Predicting house prices is a classic regression problem, and decision trees are quite well suited because they can capture those complex nonlinear relationships that often exist in real estate markets.
Yeah.
It's not always a simple straight-line relationship between, say, square footage and price. Location, age, local income levels, they all interact in complex ways.
So how does the tree handle this? Does it just output a price at the leaves?
Pretty much. The tree partitions the data based on features, like median income in the area, average number of rooms per house, etc., creating different segments. For each segment, represented by a leaf node, the tree predicts the average median house value of all the trading examples that ended up in that leaf.
Okay, so what was the setup for this one?
Again, a pipeline. First, standard scaler to scale all the input features. Then, a decision tree regressor. We started with max step 3 again just to get a baseline. For evaluation, we used cross-validation, specifically shuffle split CV with 10 splits, and scored it using negative mean absolute error.
Why shuffle split CV here?
It's a good choice for larger data sets like this. Instead of fixed folds like K-fold, it creates random Traintis splits each time, which can give a good sense of robustness. And negative mean absolute error, well, MAE, mean absolute error, tells us, on average, how far off our price predictions are in dollars, or scaled dollars here. We use the negative version because grid search CV tries to maximize a score, so maximizing negative MAE is the same as minimizing MAE itself.
Clever trick. Okay, so initial max step 3 tree. How'd it do?
The initial performance was okay and, importantly, consistent. The mean absolute error on the training set was about 0.59. On the test set, it was very close, 0.593.
Consistency is good. Means it wasn't overfitting wildly at that shallow depth. What does 0.59 MAE mean in context?
The target variable, median house value, in this dataset is often scaled, typically in units of $100,000. So an MAE of 0.6 means the predictions were off by an average of roughly $60,000. Not terrible, but not amazing either.
And the R-squared score, how much of the price variation did it explain?
The R2 score was 0.51, so that initial shallow tree could explain about 51% of the variance in California housing prices. Decent, but definitely lots of room for improvement.
So it could predict, but half the variation was still unexplained. What did that simple regression tree look like? Could you see what it was splitting on?
Absolutely. We used plot tree again. At max F3, it was easy to read. The main splits near the top were based on features you'd expect. Median income was very important. Average room size also appeared, and average occupancy, how crowded houses are in the area.
Makes intuitive sense.
Right. And each node showed the squared error, the regression impurity measure, the number of samples reaching that node, and the value, which in this case was the average median house value for all the samples in that node. You could see how the predicted average price changed as you went down different branches based on income or room size.
Okay, so visualization works for regression too. Now the big question, did hyperparameter tuning help significantly here? Could we improve on that 51% R-squared?
Oh yes. Tuning made a huge difference on this data set. We ran grid search CV, tuning mass depth all the way from 1 to 20, and min sample split from 2 to 8, again optimizing for negative mean absolute error.
And the winning combination.
The best parameters found were max depth 11 and min sample split 5.
Depth 11. Much deeper than the initial 3.
Much deeper. It suggests that capturing the complexities of the housing market required a significantly more granular tree structure.
And the performance boost. How much did the error drop and R-squared improve?
The results were substantial. Retraining with these optimal parameters. The mean absolute error, MAE, dropped significantly to 0.42, down from 0.60. So the average error was reduced from $60 K to about 42K. And the R2 score jumped impressively to 0.68, up from 0.51.
Wow, from 51% to 68% of variance explained? That's a really significant improvement just from tuning the tree's complexity.
It really is. It perfectly illustrates how finding the right hyperparameters, allowing the tree to grow deep enough but not too deep, controlled by min sample split here too, can unlock a lot more predictive power, letting the model capture those nonlinear patterns much more effectively without necessarily overfitting. They found a much better balance. Hashtag talk tag outro.
Wow, okay. That was quite the journey through decision trees. We've really unpacked them, haven't we? From the core flowchart idea, how they work inside Sklearn, how to actually see their logic with visualization.
And tackling that overfitting beast with pruning and other tips.
Right. And seeing them in action, the almost perfect iris classification, the struggle but eventual improvement on the messy abalone data, and that big performance jump on the housing prices through tuning. It's amazing how these, well, seemingly simple if-then structures can model such different problems.
It really is fascinating how breaking down big problems into smaller, sequential decisions, which feels very human, right, can be so effective for a machine learning model. And seeing the different data sets really drives home how important the whole process is. Understanding the data, cleaning it, preparing it, tuning the model.
Yeah.
It's not just about picking an algorithm.
Exactly. And that's really the key takeaway we hope you, our listener, get from this deep dive.
Ah.
It's not just about what a decision tree is, but understanding why it's useful, how you actually use it effectively in practice, and being aware of the critical decisions you have to make along the way about parameters, pre-processing, handling pitfalls like overfitting.
It empowers you to build better models, models that are not only predictive, but also, in the case of trees, often quite interpretable.
Which brings up a final thought, maybe. When you face a complex decision in your own life, outside of coding, do you find yourself sort of instinctively building a mental decision tree? Weighing the if this, then that scenarios?
Uh-huh. Maybe subconsciously.
Hmm.
It's a natural way to structure thinking, isn't it? The real challenge, I guess, both for us and for the algorithms, is how do you balance wanting simple, clear rules with needing to capture all the messy nuances and complexities of the real world? Where do you draw the line?
Food for thought, indeed. Finding that balance. Well, thanks for joining us on this deep dive into decision trees. We hope you found it insightful. Until next time, keep that curiosity peak.